What if the entire proof of the Pythagorean theorem could be encoded as a single natural number? That's exactly the ingenious idea Gödel created to prove his incompleteness theorem. The reason lies in the statement G, which says this statement is not provable. At first glance, this looks strikingly similar to the famous liar paradox. If G had been merely a sentence in ordinary language, it could easily have been dismissed as a clever play on words involving self-reference. Without G, there would be no incompleteness theorem. But Gödel constructed G as a genuine mathematical statement within arithmetic. The ingenious idea that made this possible was Gödel numbering.
Let's begin with a very simple mathematical statement. 2 times 3 equals 6. Gödel developed a way to turn a mathematical statement like this into a single natural number. First, we assign a number to each symbol used in the statement. 2 maps to 2, times maps to 5, 3 maps to 3, equals maps to 7, 6 maps to 6. This is not Gödel's actual numbering scheme. It is a simplified example designed to show the basic idea. Now the statement 2 times 3 equals 6 becomes the sequence 2, 5, 3, 7, 6. We then use these numbers as exponents of consecutive prime numbers. Calculate this and we get this huge number. A mathematical statement has now become a single natural number. And because prime factorization is unique, the process can be reversed. Given this number, we can factor it and recover the original sequence of symbols. That is the basic idea behind Gödel numbering. A mathematical statement can be encoded as a natural number. The same idea can be applied to proofs. Suppose we want to prove 2 times 3 equals 6. For illustration, let's reduce the proof to 3 simple steps. The important point is this. A formal proof is a finite sequence of mathematical formulas that follows fixed rules. And we have already seen that a mathematical formula can be turned into a number. So each formula in a proof can also be turned into a number. Suppose, for example, that we assign the number 11 to the plus sign. Then the first formula becomes the sequence 2, 5, 3, 7, 2, 11, 2, 11, 2. And we encode it as exponents of consecutive prime numbers. This natural number represents the entire first formula. Let's call it n1. Using the same method, the second formula 2 plus 2 plus 2 equals 6 can also be converted into a natural number. Call that n2. And the final formula is the one we encoded earlier. Let's call that n3. So the entire proof has now become a sequence of 3 natural numbers. But this sequence can itself be encoded as a single natural number. We use these 3 numbers as exponents of consecutive prime numbers. The resulting number is extremely large, but its size is irrelevant. The entire proof is now encoded by a single natural number p. Now, both statements and proofs are represented by natural numbers, so we can ask, is p a valid proof of n? Here, n is the Gödel number of the statement, 2 times 3 equals 6, and p is the Gödel number of the entire proof. Inside it, we find n1, n2, and n3. Decode each of those numbers, and we recover the entire 3-step proof. If every step follows the axioms and rules of inference of our formal system, and if the final formula has Gödel number n, then p is a valid proof of n. We can write this relation as proof of p and n, meaning p encodes a valid proof of the statement whose Gödel number is n. More importantly, this relation itself can be represented within arithmetic. Now consider the statement, n is provable. It simply means that there exists some proof of n. But proofs have already been encoded as natural numbers. So what does it mean for n to be provable? It means that there exists some natural number p such that proof of p and n holds. In symbols, we can write it like this. For our example, 2 times 3 equals 6 is provable means there exists some natural number p such that this holds. Provability has now become something that can be expressed in arithmetic. A mathematical statement can be encoded as a number. A proof can also be encoded as a number. Provability can also be expressed in arithmetic. At first, the question, is this statement provable, and seems to be a question about mathematics itself. But Gödel numbering transforms it into a question about natural numbers. Does there exist a natural number p satisfying a certain arithmetic condition? Now let's return to the statement g we saw at the beginning. Gödel numbering made it possible to express g as a purely arithmetical statement. This left mathematicians no choice but to take g and Gödel's Incompleteness Theorem based on it seriously. But one more idea is needed to construct a statement that, in effect, refers to its own provability. That's what we'll explore in the next video. If you'd like to see the next part, please like, comment, and subscribe. Thank you for watching.